This is the first PowerPoint over the first topic in Chem 1212 for this semester. We're going to start with a discussion of thermochemistry, and most of this PowerPoint is just an introduction to it, but we're also going to talk a little bit about the heat that can be transferred during a chemical reaction and how to calculate it. Every single chemical reaction has some transfer of energy. Sometimes the reaction is exothermic, which I'm sure you've heard of, which means that the system or the reaction itself releases heat or energy to the surroundings, or we could have an endothermic reaction, which actually takes in heat from the surroundings. But every single reaction has some change in energy. And you're probably most familiar with combustion reactions. That's how we get most of the energy that we consume here on Earth. And they're mostly products that we get from fracking of oil from the ground. The first law of thermodynamics, there are three common laws of thermodynamics, but the first law is that energy in our universe can neither be created nor destroyed. In other words, if a system loses energy, the surroundings have to gain that same amount of energy or vice versa. And so how we express that mathematically is this, that the total energy of the universe is a combination, the sum of total energy of any system you're looking at, and the systems we'll be talking about we'll define as chemical reactions, plus the energy of all of the surroundings, okay? And that overall there can be no net change in the total energy of the universe. The relationship between the energy of the change and energy of the system and change and energy of the surroundings, since the total energy in the universe is a constant, if a system loses energy, the surroundings have to gain the same absolute quantity of energy. But how we show this mathematically when we do thermodynamic calculations is you put a negative sign in front of either the change in energy of the system or change in energy of the surroundings. It would be just as accurate to write negative change in energy of the system equals positive change in energy of the surroundings, okay? So the negative just means, one side gains it and one side loses it. All right, so just to be clear on what we mean by system and surroundings, a system is anything a scientist is studying. And so for as chemists, our system is going to be the actual chemical reaction. It's the molecules or particles that are involved in the chemical reaction. And literally everything else, including the container it's in, the air around it, etc., will be the surroundings. Now, there's a couple of kind of boring definitions we have to go through, but I have seen questions like this on the standardized ACS final. So this is a good little formula to keep handy. When I was in chemistry, and what I recommend for you is that you have a little booklet or the end of a notepad where you write down all equations that we go over so that they're easily accessible for you throughout the semester. Changes in energy can be either in the form of heat, which we designate with a Q, the letter Q, or changes in energy can also be due to work performed. So what do we mean by that? Heat's pretty obvious, okay, the movement of thermal energy. Work is defined as causing an object to move. So how does a chemical system do work? It's primarily when there are gases involved in the chemical system, and a gas, if it does work on the surroundings, for example, can push, like cause a piston to move out, okay? So this is an example of the system doing work on the surroundings. The other way around, if the surroundings were doing work on the system, then the atmospheric gases would push on the system, causing the volume to decrease. So in chemical systems, when we talk about work, we're talking about pressure volume changes. And again, the only time that we would see significant work is if we had a gas involved. All right, so exothermic, endothermic, I'm sure you have heard about those before. But let's just talk about the sign convention, mathematical sign convention for those. Energy that leaves a system, so any type of energy, whether it is thermal energy or work, any type of energy that leaves a system is given a negative sign, okay? So you can think of that, if it's heat energy we're talking about exothermic, right? Heat leaving a system, we would put a negative sign in front of whatever that value is. Let's say 100 joules of heat left a system. We would say negative 100 to show that. And conversely, anytime energy is added to a system, it's given a positive sign. So for example, if work is done on a system, okay, so if you have outside atmospheric pressure pushing and compressing a system, we would give that work a positive mathematical sign. It's really important to keep up with this sign convention because one of the things that are important to chemists are to know whether overall a reaction or a system has lost energy overall or has gained it. And so in the cases where we have both heat transfer and work done on or by a system, you have to keep track of those signs to know the net result. So here's a typical type of problem using the formula we just talked about. And again, make a little note, come up with a system for yourself that you're familiar with using this equation, because again, I see it routinely on ACS final exams. So here's the typical question. You have a system, they're just giving you extra information here, okay, but it is heated up. So what does that mean? That means that heat is added to the system, right? So when energy is added to a system, what's the sign convention? It's positive, right? The system expands and does 200 joules of work on the surroundings. So this is the wording that goes along with the system is exerting energy. Okay, it's doing work on the surroundings. Okay, so that's an exothermic, exergonic type of thing. So we're going to give that a negative sign. So really in these type of problems, you just have to make sure you get your signage correct. Once you do that, what do you have so far? You have a plus 750, so that's 750 joules going into the system, and then minus 200 joules. Check your units, make sure they're the same, okay, going out. And the sum of those is the net result. So the sum, there are 550 joules, it's a plus sign, so that means 550 joules entering the system. So the system is going to end up with more energy. So it's an endergonic type reaction. So here's it worked out a little bit more methodically and more neatly, and that would be your answer. So make sure you know how to work that type of simple problem. All right, so thermal energy is a form of kinetic energy. So let's these are just some definitions you need to be real comfortable with and be able to explain, okay? Where do we get thermal energy from? Thermal energy is, first of all, heat, okay? And it results from molecules or atoms that are vibrating or moving faster. What causes the molecules or particles to move faster? When their temperature is raised. Okay, so when you supply an energy source to a system, let's say a chemical reaction, the particles, the molecules and atoms are going to start moving faster. In other words, their kinetic energy is going to increase. And as a result of that, it's going to create heat. A concept that's important for you to be aware of is that kinetic energy is directly proportional to absolute temperature. You may or may not have been introduced to Kelvin as a temperature scale. So whenever you see the term absolute temperature, they're referring to the Kelvin temperature scale. But kinetic energy is directly proportional, that's the proportional sign if you're not familiar with it, to kelvins. So as degree Kelvin increases, so does kinetic energy. Now, heat is not actually the same thing as thermal energy. It's just kind of a vocabulary game. But heat is actually the transfer of thermal energy between two systems or system and surroundings. And heat will always occur when you have two things that are at different temperatures. And that heat will always move from the warmer object to the colder object until both final temperatures are identical. When both final temperatures of things that are next to each other are identical, we say that we've reached thermal equilibrium. And this concept will be important when we start doing some calculations with heat. Now, I've mentioned endothermic and exothermic a couple of times, but we haven't really talked about it in terms of the graph that you can present, and so I want to make sure you understand that. So when chemists graph out a chemical reaction that is either endothermic or exothermic, this is similar to how they'll do it, with energy on the y-axis and progress of reaction on the x-axis. So the reactants will always be shown first, the products last, and you can see in an endothermic reaction. What does that mean? That means that the system is absorbing energy. Okay, so if the system, we'll call it reactants at this point in the beginning, absorbs energy, then the products are going to be at a higher energy, right, than the reactants. So that's true for an endothermic reaction. Exothermic reaction, the reactants are giving out energy to the surroundings, so the products are going to end up with lower energy. The two temperature scales that we'll be using in chemistry are degrees Celsius and Kelvin. Fahrenheit is what we're all most familiar with, but that's not a temperature scale that chemists use. So you are going to need this conversion between Kelvin and Celsius temperatures. That should be a freebie, easy peasy multiple choice question for you, so make sure you know that. One of the things that I always remembered when I was doing this, because I'd kind of get mixed up which of these features went on the left and which on the right, is just to remember that the value of temperature in Kelvin is always higher. Okay, your Kelvin value should always be higher. Now, interestingly enough, 1 degree Celsius equals 1 Kelvin. In other words, the size of 1 degree is the same on the Celsius and Kelvin scale. It's not the same on the Fahrenheit scale. Okay, 1 degree Fahrenheit is not equal to 1 degree Celsius. I'm not sure if you were aware of that, but I always kind of thought that was interesting. My eraser's not working very well, is it? So the other thing I want to point out about the temperature scales is that you can see here, so hold on. So the difference, for example, because 1 degree Celsius equals 1 Kelvin, the difference between, let's say, the melting point to the boiling point for water is 100 degrees Celsius, right? On the Celsius scale, water boils at 0, water freezes or melts at 0, and water boils at 100. So on the Kelvin scale, the difference between melting point and boiling point is also 100 Kelvin. Okay, so the difference in degrees Celsius equals the same difference in Kelvin. Okay, so anytime you have a mathematical formula where it's got this delta difference in temperature, it doesn't matter whether you're using Celsius or Kelvin. Okay. Here's an example of converting from one temperature scale to the other. Very easy, okay? Just mainly have to remember the formula. Alrighty, and then just plug in your values. 2.73 Kelvin. And you're trying to solve for degrees Celsius. And I don't really care if you have the 0.5 for the, it can just be 273 rounded as a whole number. And then just rearrange, okay? Degrees Celsius equals 2.73 Kelvin minus 273. So the Celsius number you're going to get is a negative number. For our purposes in this class, we will be using the terms enthalpy and heat interchangeably. Now, in reality, they're different, but at constant pressure, and that simply means atmospheric pressure. Okay, so most chemical reactions are done at constant pressure. It's only the ones that are like in a sealed system and generate gases or something that would have different pressure than atmospheric or changing pressure. But anyway, at constant pressure, enthalpy, which is designated as a capital H, is the same thing as heat. So throughout this course, again, we're going to be using these terms interchangeably. So you hear enthalpy, you can think heat, and vice versa. Let's talk about really simple systems to begin with, phase changes. Okay, so we're not talking about chemical reactions yet. Let's just melting or boiling something. So some phase changes, of course, are endothermic, which means they require input of heat, right? And so melting, boiling, and subliming. Just to remind you, in case you're unfamiliar with that term, subliming is when you go directly from a solid to a gas. You do not go through the liquid phase. That is subliming. So all of those phase changes are endothermic. And so I've always had trouble wrapping my head around the concept of an exothermic phase change. So how I remember it is it's easy for me to grasp endothermic phase changes, melting, boiling, and so I just reverse those phase changes if somebody asks me to recite exothermic phase changes. So in other words, freezing, condensing, depositing, those are all exothermic phase changes. We can pretty easily calculate the energy involved in a certain quantity of substance undergoing a phase change using a term that we call either enthalpy of fusion, which is referring to melting or freezing. Now, hopefully you realize that melting and freezing point are the same thing, right? They're just going in reverse directions. Or if we're talking about boiling something off, using the enthalpy of vaporization. Remember, enthalpy is designated with a capital H. And so these terms are easily found in a reference table, as you can see right here over to the right. I want to point out something real briefly here, looking at this table of enthalpy values. And that is the units. So if you look at, we've listed here the enthalpy of fusion and enthalpy of vaporization for a bunch of substances. Notice the units here in this chart are kilojoules per mole. Now, joules is standard for when we're talking about units of energy. but the thing that can change in the enthalpy values are the per mole. Sometimes you'll see, instead of kilojoules per mole, you'll see kilojoules or joules per gram. And so I just want you to be aware of that. Always, always, always look at units, because then if you're trying to calculate the total amount of joules or kilojoules, you'll have to multiply either by moles or by grams, depending on the unit of the standard. There's a second calculation for heat that we're going to talk about in this PowerPoint, and that is when you apply heat to a substance and it is not undergoing a phase change. How do we calculate the total amount of heat that we have added or taken out of a substance if it's not changing phases? Well, the formula we're going to use for that is what I call the MCAT formula. You can ignore these other terms, we won't use them. And that simply says, okay, the heat is equal to the mass of the substance that you're applying or taking heat out of, times C, that is, we're going to talk about that in a minute, specific heat capacity, times the change in temperature. And the temperature should be Celsius or Kelvin. Remember I said that anytime you have a change in temperature, it doesn't matter the units, whether they're Celsius or Kelvin. So before we use this formula, the new term here, specific heat capacity, I want to talk about it for just a minute. The specific heat capacity, in my favorite definition, is that it's a measure of a substance's sensitivity to temperature changes. So did you know that you can have two different substances and apply the same amount of heat to each of them, and that the temperature of one of the substances may go up way more than the other? Yeah, where's that extra heat going? Is that possible? And the example I like to give for that is all of us have been to a beach in the middle of a hot summer. And if you're barefoot, I remember being a kid and running as fast as I could because my feet were burning on the sand. And then as soon as you get to the water, it feels chilly. So if you think about it, the sand and the water are exposed to the same amount of heat energy from the sun. So why is it that the sand is so much at a higher temperature, so much hotter than the water? Well, that has to do with specific heat capacity. So this is pretty cool to compare some of the specific heat capacities. Let's find water because it has some of the highest, or it has some of the highest value. So the specific heat capacity for liquid water is 4.18. The units are really weird. Joules per gram per degree Celsius. So that's a really high value. Look at all these others. Okay. Most of the others are actually less than 1. Okay. And I want to point out here too that specific heat capacity varies depending on the phase a substance is. So look at the specific heat capacity of ice, water when it's frozen, it's lower. Okay. So what do these values tell us? Okay. The bottom line is the higher the value means that higher amounts of heat are required to change to raise the temperature. Okay? Higher value means higher amounts of heat are required to raise the temperature. So water is hard to raise the temperature. It's hard to heat up. And so that's why the water feels cool in the middle of the summer and the sand burns your feet off. Thank goodness, and that's why, one of the reasons why Earth is so habitable to life form, because it's, 70% water, and the water maintains a pretty constant temperature throughout the world, regardless of the season. And because of that, we have a climate that is temperate, that's pretty consistent. If water had a low heat capacity, that means our entire world would be as hot as the land during the day and as cold as whatever during the night. That's what happens in the desert too, by the way. There's not water around to kind of modulate the temperature swings. Here's a visual example of objects that have different specific heat capacity. So if you were to apply the exact same amount of heat to a chunk of gold and the same mass of gold and aluminum, you would notice that the gold would rise in temperature quite a bit more, I think 3 times more. I think its specific heat capacity is a difference of 3 than the aluminum. So the aluminum is much more resistant to changes in temperature, meaning that it has a lower specific heat capacity. So let's go ahead and use this in a calculation, okay? So remember, little q is our designation for heat. So make sure you write this formula down. Again, I call it the MCAT formula. It's just how I used to remember it. There's no cat in there, but if you write it out condensed, it looks like cat. Anyway, that's how I remembered it. So this is the formula that we will use when a substance is experiencing changes in temperature, okay, and not a phase change. So we have 2 formulas, right? We have one that says during a phase change, Q is equal to whatever quantity you have of a substance, whether it's moles or mass, times delta H, heat of fusion or heat of vaporization. And now we've just talked about the MCAT. Let's put those together. And it turns out, this is very interesting, this is called, well, it's kind of loosely, a heating curve. So if you start out with any solid material, so let's just think ice, okay, and you apply energy to that system, what's going to happen? Well, eventually the solid is going to melt and you're going to get a liquid. And then if you keep applying energy, obviously, you can forget about plasma, obviously you're going to boil off a liquid and make a gas. But what's interesting here is the shape of a heating curve. So let me see if I can erase that real quick. Notice that it's like steps, like stair steps, right? It's not a smooth curve. And so we have plateau areas and then we have sloped areas. So it's important to understand what each of those areas represents. The flat areas are phase changes. Okay, the flat areas or plateaus are phase changes. And during a phase change, there is no temperature change. Okay, so where's the energy going, right? We're adding energy to this system, and during a phase change, there's no change in temp, so where's the energy going? The energy is going into loosening or breaking up the intermolecular attractions between molecules. So just real quickly, let's say we're talking about water, and I'm hoping you remember intermolecular forces from 1211. If not, you're going to want to quickly review that. So we have these intermolecular attractions between water molecules, and so what happens when you apply heat is that, of course, molecules begin moving faster, right? They vibrate faster and faster and faster, and when enough heat has been added so that the kinetic energy or movement of the particles is large enough, then the intermolecular attractions that hold them close to each other will be disrupted and it will change phases. And so that's really all that happens during a phase change, is that the intermolecular forces are loosened. And that's where all the energy is going. So the energy, rather than going to raise the temperature, during a phase change, it's going to loosen the intermolecular forces. All right, and as a reminder, during a phase change, we obviously cannot use the MCAT formula. Why? Because during a phase change in temperature is 0. So that QMCAT formula becomes meaningless during a phase change. And so the formula we want to use to calculate heat during a phase change is the one that uses enthalpy, okay, either of vaporization or remember the other one was enthalpy of fusion, which means melting. And so you would be given the delta H values, the enthalpy of fusion or vaporization, and you would simply have to multiply that value you were given by the number of moles or number of grams of the substance you have. So again, pay attention to the units for the enthalpy of fusion or enthalpy of vaporization. Okay, as I said before, sometimes the units are joules per mole and sometimes joules per gram. But whatever the units are, make sure you multiply it by the quantity of substance in the correct units. All right, so let's put this all together. And let's say that we have a substance like water, and it's in solid form, it's ice form, so maybe this looks like it was like minus 75 degrees or something to begin with. Then we start applying heat. And of course, like you would expect, the temperature of the ice is going to start increasing until it reaches the melting point for water, for ice, 0 degrees. And then during the phase change of melting, there's going to be no temperature change, right? Then once it's all melted and we have a liquid, the temperature will start increasing again until it reaches the boiling point, 100 degrees, at which point temperature stays constant until it's all boiled off. And finally, once we have it all boiled and we have complete vapor phase of water, the temperature as steam can keep rising again. And so if you are doing heating curve calculations, which you will be expected to be able to do, you will use both of the formulas we've talked about, and you will have to know when to use each formula. Now, let's say that I asked you to calculate the total heat involved in heating a chunk of ice from minus 75 degrees Celsius all the way up to steam at 175 degrees Celsius. How would you do that? It turns out that you have to do separate calculations. Every single leg of a heating curve has to be a separate calculation because there are different formulas. So this particular one would require 5 calculations, and then at the end you just add them all together. So let's go through an example. Alrighty, so let's work a sample problem. How much energy would it take to convert 1,250 grams of snow, which is another form of frozen water, from minus 18 degrees Celsius, and whoops, I see an error. That's supposed to be 110 degrees Celsius. All right, so that's all 5 steps of a heating curve. Okay, first step is heating the snow to the melting point. The second step is actually melting the snow. Third step is warming up the water, liquid water. Fourth step is boiling the substance off. And the fifth and last step is heating the steam. So we have to do each one of those calculations. Remember that if you are raising the temperature, you're going to use the MCAT formula. If you are undergoing a phase change, you're going to use the other formula. Here are each of the 5 steps, plugging in the values, mass. You must be given specific heat capacities, okay? Please remember that the specific heat capacity is different depending on the phase of matter. For example, in step 1, it's ice or snow, right? That's frozen water. So the specific heat capacity for frozen water is 2.04. But for liquid water, the specific heat capacity is 4.18. So be careful, okay? And then again, change in temperature, it's only for that step 1. Remember, every leg of that heating curve has its own values. And so when you're going from negative 18 degrees frozen snow to its melting point at 0 degrees, there's only an 18-degree change in temperature. And again, remember that anytime you have a phase change, okay, so melting is one phase change, boiling is the other, that you are going to use the delta H value, okay? For melting, it's delta H fusion. And notice that the units given to you are joules per gram. So that means that you have to multiply it by the grams of substance to get the joules. And down for boiling, you're going to have to use delta H of vaporization. And again, the units are joules per gram. Anyway, once you have the joules for each of the 5 steps, you're going to add them, and that will give you the total heat involved in taking that chunk of ice from -18 up to 110 degrees. That is it for the first PowerPoint. So I recommend working on the worksheets right now, the practice worksheets that have to do with calorimetry.